Well, let's see. It's about time to get going here. Has anyone had a chance to look at the um, resistivity lab material yet? And did I get everything onto that should be there?
I took a look at it last night.
Okay.
Um, what is the length of the number 28 NS wire?
Um, which one? Uh,
The 28 gauge NS wire. It's you have like the 5 lengths of the 30 gauge NS wire,
oh,
and then the next problem asks us to look at what the resistance of the of the 28 gauge is, but
oh, uh,
no length is given.
let me look at my pictures of those things. I think I've got them in here. Let's see. Or did I? I hope I took a picture of it. Let's just, let's see. Okay, I've got my card out of my camera attached to my computer right now, and I haven't deleted the pictures yet, fortunately, so. Um, 30. Oh, you can't see that. I'll drag it over here. These are just all the measurements I was taking with things, but oh, wait, was that it? Hide your eyes.
And we can't see it anyway.
Oh, okay, good. Anyway, it's 200 centimeters of number 28 NS wire is what it happens to be. Yeah.
And then the next problem asks us to compare it to the measured resistance, and that wasn't on the slideshow either.
Okay. Well, let me do my sharing routine here again. Let's see. Share number 2. Oh, that's not it. That's the 30 gauge again. Here's the oh, that's still number 30 gauge. Here it is, number 28. So 200 centimeters of number 28 has a resistance of 7.286 ohms.
And part of the lab also mentions like a second spool of 30 gauge. Is that just not on there?
Oh, a second spool. Yeah, I only did one. And
Okay, the 200 centimeter 30 gauge. Okay.
yeah, I thought I'd edited that out of there, but I guess I didn't. Yep, there's only one spool of that. So that was those things. Something I wanted to start with today was talking about a velocity selector. And this is something that kind of an interesting gadget. I first heard of one when I was in graduate school, my first year. I was interested in working for a research group that studied atmospheric physics. And what they would do is fly instruments on balloon flights, these giant helium balloons that they launch from, oh, let's see. I can't remember if it was Paradise, Texas or Palestine, Texas. One or the other. There's a launch facility there. And they'd fly them up to like 100,000 feet or 150,000 feet, way up there. And then they'd take measurements for a while, and then they'd drop them back down to the surface of the earth with a parachute and recover the instruments, hopefully. Although while I was in graduate school, I heard of one guy whose he'd spent like 3 years working on this instrument package that was going to fly on the balloon, and the parachute failed on the way down, and it was just a mass of wreckage when it got there. And that could be kind of scary, because 3 years working on that was probably after his first 2 years of taking classes. And so that's 5 years of into graduate school, and might be kind of scary, but they let him write a thesis strictly on the instrumentation that he had built. And every once in a while they do that. I was a little worried about that my last year in graduate school, because the hypothesis we were testing was to calculate the likelihood of this one thing happening, which was that a grazing collision that something might undergo, that a nucleus could undergo in a grazing collision, would possibly stretch it into a long-lived, elongated state that'd be sort of football shaped or a long ellipsoid kind of thing. And it was to try to explain some experimental observations. And in fall of, I guess it would have been my fall of my 5th year in graduate school, I had finished the calculations to get the likelihood, and I was basically getting likelihoods of 1 chance in 10 million. And we were expecting to explain the observational data. It would have been had to have been about 50%. And so 1 chance in 10 million is actually pretty much 0. And that's round off error is what it is. And I went and talked to my advisor about it, and he said, nope, you can still write a thesis on that. Most of the time what we get are null results. So I got a thesis based on a null result. And yeah, that was a relief. But anyway, this one year, the first year I was in graduate school, I was interested in this atmospheric physics group, and I kind of think I would have maintained my interest in that longer than I'd maintained my interest in the nuclear physics stuff that I was working on, which didn't last beyond graduate school. But this research group, one of the things they would fly up in these balloon flights were something called a mass spectrometer. And the first stage in a mass spectrometer is something called a velocity selector. And what it does is it lets only particles through that have a particular velocity. And so they use electric and magnetic fields. And so it's a region where, let's see, I'll try to make this look reasonable here. Okay, so, and then I need to have a kind of a dashed line here that's going to represent the path of the particles that have to get through. And at the left opening of this thing, that's where this velocity selector would be exposed to, say, the atmosphere at 100,000 feet or whatever it happens to be. Oh, and something that they would have before it got that far is an ionization chamber. And we can just kind of draw that as a little box. And there'd have to be an opening on it as well. But and the ionization chamber is just a place, particles are allowed in here from the atmosphere, and particles are going at a good clip, you know, typically 500 meters a second, but that's just the RMS speed. There's a whole range of them. But in the ionization chamber, there would be something like an electron beam in here, and the electron beam would be shooting sideways, and its purpose is to knock electrons off of the atoms that come into here. And so now they're charged. And typically they would, or at least the ones that they're interested in, would have a charge of plus E, having lost one electron. It would be very unlikely that an electron would attach itself to an atom, but that would give it the opposite charge, and minus E instead of plus E. So that wouldn't be likely. It is possible that, actually probably not. They could control the energy of the electron beam so it would not be energetic enough to knock a second electron loose from an atom. The first electron it could knock loose would be the least tightly bound electron to the atom. And once that electron is knocked loose, the next least likely, or next least tightly bound electron, I guess, would be much more strongly attached to the atom than that first one was. And so it would be difficult to doubly ionize the things, although it could happen once in a while. But turns out when it gets out into the outer chamber, it might not behave as well as they want it to. But anyway, in this region of the velocity selector, they would have a magnetic field, and the way we indicate a magnetic field that's into the page is that we just have a whole series of X's. And this would be a uniform magnetic field in here. And these things are actually a pretty small volume of space. Is the entire mass spectrometer thing is not that large a device. And, you know, like this big, maybe, for the entire thing. And that's the volume of space. And for something that big, it's not that difficult to make a uniform magnetic field in a small part of it. And this, it would be uniform in here, and then it would extend out into the rest of it. Now, if you've got positively charged particles that are coming into here, I'm going to rotate this for a second. If they're headed in that direction, and I'll put a note up here, B into page. Okay, so positively charged particles, they would have a force on them that would tend to drive them upwards. And so that would be the magnetic force on any positively charged particle in here. So this would be F sub B in that direction. And let's just imagine that this is one of our positively charged particles. Well, you want to filter out the particles that have a particular velocity, and the F sub B is going to equal Q V cross B. So it'll be something like that. And it'll have a magnitude in that direction of QVB, because the velocity will be perpendicular to the magnetic field. So we have that. But we want that to be balanced by an electric force. And so we'd have an electric field. This would be, whoops, I'll just call it QE, would be a force in the opposite direction. And you want to select for a particular velocity. And so you want that one to just be QE, and you control the strength of the electric field. Now, the way you'd make that electric field is to have positive charge on a plate up here and negative charge on a plate down here. And this is actually, imagine shrinking this way down. So it's a pretty small volume of space. But F sub E then is just going to be QE. And this will end up being QVB. And if we let this be the Y direction, it would be QVB in the J hat direction. This would be QE in the minus J hat direction. Well, we want the sum of the forces to be 0, and so we'd have QVB minus QE is equal to 0. And the Q's actually divide out, but you find that the electric field just has to be V times the magnetic field, and you select the value of the speeds that you want them to have, and then just control the electric field that way. Your magnetic field is usually something you set at a particular value and just leave it that way. But then the selected velocity is just the ratio of E over B in the case of this thing. And so if you want your particles to have a velocity of 497.3 meters per second, you pick an electric field value that will give you that. This is just the velocity selector. So the particles that get into here are only those that are traveling straight along this line. And you would have these two openings small and narrow and lined up with each other. So something has to be moving right along that line. And now it has to have a particular magnitude to its speed as well. Then it gets into the mass spectrometer as a whole. And so we're going to adopt a different scale here. In the mass spectrometer as a whole, you have this thing in here. Here's where the velocity selector was. And then there was the little ionization chamber attached to that. And in the mass spectrometer body itself, there would be a bank of, well, let's see, you'd have a uniform magnetic field in there. And so it's the same uniform magnetic field that you had in the other part. And it doesn't look like the way I'm drawing it, but just pretend it is. So again, you'd have B into page. And so particles are coming in here. And the positive ions come into here with a particular velocity, and now there's no more electric field acting on them. So that V cross B force that's always perpendicular to their velocity will make them travel in semicircular arcs. And so they'll do something like this. And then along this wall of the detector are narrow little electronic slots that they can end up in. And the radius of their path, well, you end up with the force acting on them is QVB, and that will equal MA, but in this case, it's going to equal MV squared over R. And you can determine the mass of these particles because you selected the velocities of them, and the radius of their path of curvature, or the diameter of it, determines how far along here they'll be and which slot they happen to land in. So you've got a bunch of different slots here, and they're much narrower than what I've drawn here. And the mass that comes out of here, let's see, we would have, that V is going to be gone. You'd have Q, which is going to be plus E, B, R over V, I think. So the more massive they are, the bigger the radius of curvature is going to be. And these things have been used for, oh man, a long time. I know at one time the University of Minnesota was known for this way back in the 1940s, was not on balloons, but for mass spectroscopy of getting nuclear masses. And with a laboratory one, they were much more precise than the ones that got flown on balloons. But the laboratory ones, they could get 5 or 6 significant figures on nuclear masses with those things. And so it's a pretty precise way. And they're used in, other fields of study today. I can't remember off the top of my head, but every once in a while you'll hear the term mass spectroscopy applied to something where it was studied. My 2 friends that worked in that lab, I kind of envied their field. It was more fun than what I was doing, which is mainly computer programming. And they also, both of them got hired by NOAA when they finished graduate school, which was the National Oceanic and Atmospheric Administration, for doing climate studies. And one of them became the lab director of their laboratory down at on Mauna Loa in Hawaii, where they measure atmospheric CO2 and pollutants in the air and all kinds of stuff. So it was kind of neat work anyway. Let's see. I think, here we go. Yesterday we were doing a little bit with drift velocities and charges moving in currents and things like that. And I want to continue on with that today. And eventually today we're going to get to the point where we'll consider the magnetic forces that are on these things. But I wanted to do a couple more, or maybe at least one more example problem having to do with this. And silver isn't necessarily a practical conductor, but it's a really good conductor. A silver wire 2.6 millimeters in diameter, which is a pretty fat wire, actually. That would be pricey stuff too. So it'd be about that thick. And but it transfers 420 coulombs in 80 minutes, which isn't an awful lot. Now, this one actually gives us the number of free electrons per cubic meter. So that's kind of nice. What is the current in the wire? And what's the magnitude of the drift velocity in the wire? Well, the current is just, we use the letter I for current. It's just going to be delta Q over delta T. How much charge happens to flow? Well, it's 420 coulombs. And then 80 minutes, I'd take 80 minutes times 60 seconds per minute, which I think ends up being 4,800, pretty sure. And I get about 8.75 times 10 to the minus 2, and it would be coulombs per second when I'm done. And coulombs per second are amperes, so 8.75 times 10 to the minus 2 amps is the way you'd describe that. So not a huge current. I guess you could also write that as 87.5 milliamps. So this isn't terrible. It's just an experiment. So what's the magnitude of the drift velocity in the wire? Oh, the last question is going to make us think here, but that's all right. The drift velocity, we can use our current that we had yesterday. It's NQA V sub D, actually. Oh, here it is. There it is. Yeah. And the Q is just the charge on the electron. So the 1.60 times 10 to the minus 19th coulombs. And so the drift velocity we can solve for here, which we did yesterday. and something. It's the amount of current divided by, oh, let's see, NQA. Okay, well, we can just plug all the numbers in here. 8.75 times 10 to the minus 2. I'm going to leave this as coulombs per second. And then down here, my N is that 5.8 times 10 to the 28th electrons per cubic meter. And I'll actually just write that as meters to the minus 3, because the electrons are just a placeholder word. This will be 1.60, the Q, 1.60 times 10 to the minus 19th coulombs. And the area will be pi times that diameter squared divided by 4. Oh, let's see, 2.6 times 10 to the minus 3 meters. Okay, now are the units going to make sense? Meters squared here times meters to the minus 3 will leave you meters to the minus 1. That's 1 over a meter on the bottom. It'll come up top as a meter. The coulombs divide out, and I'll end up with meters per second. So that's good. That's a drift velocity, if ever there was one. So, but it's going to be kind of messy. And I want to be careful to wrap that thing in parentheses. So okay, and I get at least, let's see, I've got 2 sig figs. So 3.7 times 10 to the minus 6th meters per second. So not particularly fast, which would be 1.3 centimeters per hour. Okay, so they're just kind of poking along there, move that far in 1 hour. So it's faster than fingernails grow, but not terribly fast. Okay, and then how many free electrons per atom of silver are there? Well, let's see. If I figure out the number of atoms per cubic meter per silver, we'll start with that. The density of silver is 2.3 times 10 to the third kilograms per meter cubed. So and then the molar mass of silver is that. So that would be 0.10787 kilograms over, whoops, I'm going to get the reciprocal of what I want, but that's all right. Yeah, I can fix that. I want the density or the mass on the bottom. And then that's per mole, which is 6.02 times 10 to the 23rd atoms. And so the kilograms will go away, and what I'll get is atoms per cubic meter here. And if I just divide the number of electrons per cubic meter by the number of atoms per cubic meter, that'll tell me how many free electrons there are per atom. So 10.5 I think this is dimensional analysis. I'm not sure. It's using a bunch of ratios that you have to figure out something. That's what I think of as dimensional analysis anyway. I don't know if okay, as far as atoms go, I get 5.86 times 10 to the 28th atoms per meter cubed. And actually, we had 5.8 times 10 to the 28th free electrons per cubic meter. Those are essentially the same numbers, pretty much. And so it looks like for silver, there's about 1 free electron per atom. This is a slightly smaller number than this one, but I'm not sure that's significant or not when we've only got 2 significant figures on that one. So anyway, silver's got about 1 free electron per atom. Okay, and we don't need to repeat a calculation. It's almost like that. Let's think about the force on an electric current that would happen in a case like this. And I'm going to start with another drawing here. Hang on a sec. My wife's mother is visiting, and she's the great-grandmother of my granddaughters, and they're talking to them on the phone, so they got excited. Anyway, let's imagine that we have a wire that has a current flowing in this direction, so that way. And I'm going to imagine that I'll consider a small length of the wire, DL, and it's in an external magnetic field. So we'll just imagine that we have this going on. And the magnetic field that's into the page here, but the current is going in that direction. And if we imagine that the charge carriers are electrons going in that way, let's see, V cross B would be in that direction, but when you multiply that by a negative thing, there will be a magnetic force down in this direction. And on average, the charge carriers will have a drift velocity in that direction. And so within this little volume of space, and let's imagine that this has a cross-sectional area A, so ADL will be the volume of this little chunk of wire that is carrying this current, and that's a volume. If we had things in everything measured in meters, we might have a bunch of 10 to the minus something or others in there, but that's okay. That would be a volume. If I multiply that by the N, then that'll be the number of charge carriers that are in there. And if I multiply that by the Q, then that will be the current that's actually flowing in there. But let's consider the charge on this whole chunk of wire that these charges are moving in. First of all, on each individual atom that's in there, we'll have a force that's going to be Q V sub D. Let's see, I forgot a V sub D on there. Oh, that's the total amount of charge within this volume is what that is. But I'll have Q V sub D crossed with B. So we've got a magnetic field that's into the page here. And so with negative charge carriers, the charge on each one is going to be, I'll just call it F sub B. And that's just on a single charge. We've got a whole bunch that's in there. And so that's the force on one charge. But I want to know the force on every charge that's in here. Well, actually, the NAD sub L is going to be how many charges are within that volume. Here's the volume, and N is the number of charge carriers per volume. So the total magnetic force on this chunk of wire, which I could call DF, and I'll write it as a vector here. It's going to be a downward force on that, is going to be this thing times the number of charges that I have in there. So it'll equal NADL, let's see, times QV sub D cross B. And some of this stuff, if I just go for the magnitude of it and recognize that V sub D is perpendicular to the magnetic field, then the magnitude of DF is going to be N, I'm going to rearrange things, Q V sub D. I think your book uses a lowercase d for the drift velocity, but I'll just stay consistent. V sub N Q A. I don't remember what order I'd write these things in. NQA, got those. V sub D, got that. And now I've got DL and B over here. So this is just the current. And so NQV sub DA is the current that we've got in that wire. And the force that's on that little chunk of wire is going to be the current times its length times B. And if we choose to define a, now this would be defined in terms of a positive charge going the opposite direction. If you imagine instead that you've got positive charges going that way with a velocity V sub D, the force on them, QV cross B, is actually in the same direction. So it ends up not really mattering a whole lot. But if I imagine that I have a little length vector for this particular thing, DL, define DL to equal the magnitude of that, but if I let this be the I hat direction, the direction that the current is flowing, then that force can end up equaling this. DF will equal I, which is all this combination of stuff, DL cross B. And that would be the force due to an external magnetic field on a small current element carrying a current I. And we'll imagine that the charge carriers are positive going in one direction. Turns out if it's negative charges going in the opposite direction, you get a force that's in the same direction, of the same magnitude, and you can't actually tell the difference except for one particular experiment that I'm going to talk about. But anyway, that's the magnetic force on a current element. And if you happen to have a situation where you've got a uniform magnetic field and a long wire in there, every bit of that long wire in this external magnetic field, if it's uniform, will have a force in the same direction. And in this case, if this has a length L that's going in this direction, you can choose a vector L to point in the direction of the current flow, and the total magnetic force that'll be on it is going to be, let's suppose that I goes in that direction, and so that's our direction of an L vector. It'll just end up being IL cross B. Now that's only good if you have a uniform magnetic field, which you might sometime, and it's uniform over the straight length of this thing. If you start putting curves in this, the direction of the force ends up being different for every part of the curve, and things can get a bit more confused on that. Before we look at a couple of applications of this, I want to introduce something that demonstrated what the charge carriers were, and it's something called the Hall effect. And it was something that they did with a flat ribbon of wire. You had wire that's pounded into a flat ribbon, sort of like this, except it would actually be possibly much thinner than this. And you have an electric current going through this ribbon that we have here. And I think for the original Hall effect, maybe it didn't, this might be thin enough to actually demonstrate it, but whoops, spell it right. Let's see. So a flat and thin conductor. And let's imagine that the charge carriers that are in the wire are actually positive things that are moving in this direction. And you put it in an external magnetic field. So this will be a B field into the page again, because it's easier to draw than anything else. So B into page. All right. Now this one, we're not worried about the external force that this does on the current as a whole. This thing would be clamped down somehow, but we are interested on what'll happen to these individual charge carriers in here. If they're positive charges moving in this direction, then the force on each of the individual charges, or on average with their drift velocity, is going to be QV cross B, and it'll be in that direction. And we can just put a V sub D on those things. You'd end up with some positive charge building up on this part of the flat thin conductor, our ribbon conductor, and you'd have negative charge showing on this side. Okay, those flat charges leave behind whatever was in there. And if you hooked a voltmeter up to this thing, it would show this side to be at a higher electric potential than this side, because within this conductor, you're going to have an electric field that points from left to right, and the electric field points in the direction of decreasing potential, and so this would be the high potential, this would be the low potential. But what if it's negative charges going in the opposite direction? What's going to happen? So with this conductor you've got, let's suppose we have negative charges that are on average headed in this direction, V sub D, with a velocity V sub D, and we still have this external magnetic field. And these negative charges in there are somewhat free to move. That's what the current is composed of. So we have that. Well, for a negative charge, the V cross D part is going to point that way, but then you multiply it by the Q, which is negative, and if this is what's going on, you'll end up with negative charges building up on this side of the conductor and positive on this side. So if you hook a voltmeter up to this, you'd have this side being at a higher potential. Now, if it was positive charges going that way, you had the left side at a higher potential. If it's negative charges going the opposite direction, you'd have the right side being at the higher potential, and this was found to be correct. Now, it makes sense to us now that we have an atomic model of what's going on here, that the protons are going nowhere. Their atoms are locked into the crystal structure of the metal, the solid structure of the metal, and they don't go anywhere. But those outermost electrons on those conducting atoms are free to move around, and those are what comprise the electric current. But this is the only place where it matters what the charge carriers happen to be, at least in solid conductors. If you've got a beam of electrons in a vacuum or in a mercury tube or something like that, that makes a difference. But as far as wires are concerned, it doesn't matter if it's a positive charge going one way or a negative charge the other way. The only time that shows up is you have this nice flat and thin conductor, and we just don't do stuff like this except in this particular experiment. After the Hall effect was discovered in the 70s and 80s, people started investigating thinner and thinner conductors where you could start treating them as a single layer of atoms. And something they discovered was the quantum Hall effect, where the thing was quantized somehow. And then later there was a fractional quantum Hall effect that was fractions of the original quantum Hall effect. And I can remember hearing a talk on it in grad school and can't remember what it was. It was the person who'd gotten the Nobel Prize for the fractional quantum Hall effect, or one of the Nobel Prize winners. And usually by the time they were 5 minutes into their talk, they were, unless you were specializing in that particular field, you didn't know what they were talking about. So it was pretty hard to follow most of those talks, but it was neat to see them. Some of them were good speakers, even if you didn't know what they were talking about. So there's that, but let's explore these two relations here for a few problems and see what we can do with this. dF is IDL cross B. We'll probably just be using the F equals IL cross B here today, because I think we're almost out of time. Let's see, a horizontal rod with a mass M and length L is aligned in a north-south direction. I wish, I don't know where I copied this book out of, or problem out of, but the direction here doesn't matter as far as the Earth's geography happens to be, because we're talking about an external magnetic field we're going to apply, not the Earth's magnetic field. So, but anyway, the rod carries a current I in the direction toward the north. When a uniform magnetic field B is applied to the entire length of the rod, the magnetic force on the rod keeps it suspended at rest in midair. Okay, well, let's look at this thing from the side and imagine here's our rod, and maybe it's, I don't know, got a wire on it or something like this going down to some kind of a battery or something like that, or a power supply. So we'll have a current going in this direction, and we let the L vector point in the direction of the current, and this will have a force on it downward of mg, So we need to have a magnetic force that is on this thing that's in the upward direction. And so this would have to be F sub B, because somehow this thing is hovering in midair. And we want to know that. So find the minimum magnitude that B can have. Well, in this case, that F sub B is going to equal I L cross B, and pretty much all we know is I and L. We just have letters for this thing. But magnitude-wise, it's going to equal mg. And so I can say ILB will equal mg, and the minimum magnitude B can have is going to be mg over IL. Now, how do we get the force to be upward in that direction when we've got the current going that way? Well, start playing with your right hand, and if L is into the page, IL cross B will point upward. And so you'd have to have that the magnetic field here is into the page. By the way, if we had to have a sine theta tagged onto this term, the most sine theta can ever be is 1. If it's any less than 1, that sine theta would end up being down here. And if it's less than 1, then you'd have to have a bigger magnetic field for this. So the direction of the magnetic field then would have to be, well, north is that way, south is that way. If we're looking with north on our right, we'd be looking west for the magnetic field. So that would be the direction that it has to be in that case. Okay, I think all the other problems I have will take at least 10 minutes, so I'll stop there. Monday, we're going to look at more forces on currents, and in particular, we're going to look at the torque that can happen on a current loop. We're going to look at the specific example of a rectangular current loop, but the result we get can be extended to a planar current loop of any shape. It's just harder to show it. We could potentially calculate it for a circular current loop, but it's just easier to deal with the rectangular current loop. And so we'll do that. And then we'll just extend the idea to a circular current loop. And so Monday, torques on current loops, and then we'll also introduce the idea of a magnetic moment. And this is something that has applications in lots of different areas, but that's what we'll be doing Monday anyway. And I'll try to remember to put up an announcement with that, or maybe I'll add to the page for the resistivity lab and let you know what the measured resistance and length of the number 28 NS wire happens to be, for those of you who weren't live watching this. I don't know, maybe I recorded that. I think I did. Anyway, that should be, yeah, we were live. I think I was recording this from the word go. So I'll just make a note at the bottom of that lab. Watch the first 5 minutes or so of Thursday's video to find out that value. Okay, any questions? Otherwise, have a nice weekend.